for each partition of n lambda and mu such that lambda by mod mu is a horizontal strip, we have an eigenvalue one by n squared of mn given by 1 by n squared, that's the overall prefactor, times the size of lambda plus 1 choose 2, which is n plus 1 choose 2, but I'm writing it this way just to keep the similarity between the next term, minus the size of mu plus 1 choose 2 plus diag of lambda mod mu. So the diag is the sum of the contents now of this Q shape. You don't take the entire partition, but you take lambda mod mu. Yeah, you take all the contents of with multiplicity. Given by f lambda d mu, where f lambda is the number of standard Young tableau of shape lambda and d mu is the number of this désarrangement tableau of shape mu. So
these numbers available on the OEIS?
I don't know, that's a good question. I didn't check. We can check in the discussion hour in 5 minutes. Yeah, I don't know. Yeah, I don't even know in what context they are studied. But this, so the proof.
If it is there, we can get some info.
So
it's sigma f lambda d mu sum over all possible
right.
valid pairs will be in fact.
Yes. But there's a lot of condition. Lambda mod mu should be diagonal, horizontal strip, and so on.
That itself is not.
Yeah, no, nothing is clear. Yeah. So the
Yeah,
So we have an eigenvalue. These are the only ones, or there are still more?
no, these are the only ones. And in fact, some of them could occur with multiplicity 0, in which case they do not occur.
looks highly related to that Young semi-normal form.
Is it?
This désarrangement.
But have you seen these désarrangement things before?
No, but in Young
Huh?
semi-normal form, derangement.
This should be related to derangement. But
There's a disarrangement for permutations, exactly the same, as it is even. That the cardinality of such permutations, now with first doesn't being even, is equal to dn, and that's Desarguin's motivation to define this.
I see.
There's a recurrence for it, another recurrence for it. dn is in fact n times dn minus 1 plus minus 1 power n.
Okay,
To prove that this is a good set.
I see.
From here, this is the counterpart for tableau.
So you have seen it, this kind of definite.
Permutation.
Okay. Now, what were you saying?
No, saying when you look at the action of Young semi-normal form, when I and I plus 1 are neither in the same row or same column. These are some of those special cases, I mean. So maybe.
No, they can be in the same row.
Same row and same column.
They can be in the same row, they cannot be in the same column.
No, even the same row, but cannot be in the same. But anyway, what I'm saying is.
Okay, maybe.
Lambda could be equal to mu. But if it's 0 here,
Then
the eigenvalue is 0.
That's good.
Multiplicity.
So maybe, so for each lambda and mu, each lambda you will get this thing. So good point. So let me just state some corollaries of this and then.
So how does this show that
I'll just describe it. That's what I was going to. So he gets all eigenvalues this way.
I mean, are the eigenvectors what is
Yes. So they write down so part of the reason the paper is so big is that they write down the eigenspace decomposition, and they say it's very nice, but it's a pain to read, and it's quite complicated actually to write down the eigenspace decomposition. So corollary of this is that the second largest eigenvalue corresponds to lambda equals n minus 1 1 and mu equals 1 1, and we get 1 by n squared, n plus 1 choose 2, minus 3 choose 2, plus 1 plus etc. up to n minus 2, and if you simplify this mess, you get n minus 2 times n plus 1 by n squared. Okay, so this gives the second largest eigenvalue. But they do more actually than what we have studied. So we have looked at permutations, right? I mean that was the original, or rather Diaconis looked at these things. So what they did was they looked at all possible words. So you can define this random to random chain for words with M11s, M22s, and so on, right? You just take something and put it somewhere else. And then it boils down to looking at semi-standard tableau. So if you look at the statement there is another partition new that comes in, which is the content of the tableau and so on. So they have done something quite general. Everything uses this Fourier transform, going to the representations and analyzing it carefully. But I have not been able.
Representation theory word is only of Sn.
Only of Sn. Yeah. So I have only stated this for random to random on Sn, but even it works in general. Yeah. And as a corollary, they get the second largest eigenvalue. Now the challenge would be to use this formula to prove cutoff. Just like random transpositions, there would be you would really have to understand where this measure is concentrated. I mean, when we have this Plancherel formula, we use that to get a sum, where that sum is concentrated, and carefully doing the inequalities and so on. But that would be the next challenge in this business.
I'm sure they are already
working on it. No, Franco and these people, they're not as good as Percy and these inequality analysis. I mean, it was very delicate, remember, even for random transpositions. So it's not clear to me that it would be that easy. But anyway, okay.
true.
Yeah.
But once you have this, it's you have to go for that.
Yeah, then at least, we should be able to see 3/4 n log n coming up somewhere. Yeah.
So other than the cutoff, are there other maybe lesser
Lesser?
things to aim at? I mean, other open problems.
For this shuffle? I don't know. I don't think so, but I mean, people have, so I mentioned these probabilistic arguments that improved the mixing time bounds. They're very sophisticated. Techniques are extremely hard for me to read. They use all kinds of comparison inequalities and things like that, which are so very technical stuff. But I think you will get the right sort of upper bounds only using this theory. This is my guess for the mixing time. But I don't know what other questions there are. So that people have looked at.
Now
Okay, if you like.